I think we can start this webinar. So good evening and good morning, everybody. So I'm Christophe Jorzak. I'm a founding partner at Quantonation, VC fund dedicated to deep physics and technologies and quantum technologies. Sorry, and I'm based in Paris. So we're having this online meetup from the Lab Quantique. I'll go into that a little bit later, tell you who we are, sorry, and what we will talk about today. First, a couple of ground rules about how this will work. So for those who have practiced Zoom extensively these last weeks, and I think that's the case for most of you, this is slightly different. This is called Zoom webinar. So attendees can't broadcast their videos. We don't see you. Though you are seeing the panelists. At the start of the session, everybody's muted. If you raise your hand, and I see it, in principle I should, I'm the host, I can grant you permission to talk, although that's not necessarily the easiest for interaction. I think the best is to use the Q&A window that you should have on your screen somewhere. So you can ask questions. Questions are public comments are authorized, and you can also upvote for questions. The panelists will answer your questions, and I think that's the most effective way to go. We will share slides and videos later once we're done with the session. Okay, so we reached 100 attendees, which is pretty cool. Thank you very much for taking the time to be with us today. So first, maybe to start with just a few words about Le Lab Quantique and who we are. So Le Lab started in Paris as a meetup in 2018 with several events that we've organized since then. And I showed a couple of pictures on the left. So we've had meetups, traditional ones in the evening. We've had hackathons, quantum computing, quantum networks, several social events. We're also associated by BPI France to the organization of high-profile conferences and workshops. Quantum computing last year, quantum cybersecurity just before lockdown 2 weeks ago. And by the way, I use the opportunity to announce that BPI is organizing a conference in principle in June, and we'll share the information with you as soon as we've got, of course, more information. And I'd like to mention here les Trois Mousquetaires, so people who are working with me on this concept: Jean-Gabriel here at Quantonation, Jean-Christophe Goujon, BPI France, and Romer Marino from Deep Tech Founder. So next slide is about what we want to achieve. So we've got pretty ambitious ideas about how to make the Lab Quantique to go into the next phase. We think it's been pretty successful to create or to gather an ecosystem of quantum technologies in France, about 700 people and more. If I had over a list, let's say 1,000 people engaged into this ecosystem here. So we are working on expanding the concept and turning that into a not-for-profit think tank in support of a global ecosystem with several aims, several ambitions in terms of foster the emergence of talents, also help startups grow and interact in particular with industry for proof of concept projects, for example. So we've been involved, each and every one of us, the four of us, pretty much in working with startups for quite some time. And I think there's something that can be done for this kind of not-for-profit. So if you want to collaborate with us, so whether you're a company, institution, feel free to contact me. We're working on this concept right now, and we plan to be operational by June or slightly later, depending on the situation, obviously. So next, I'd like to introduce our panelists, which I thank very much for taking the time to be with us today. So again, it's a first that we do it online. Usually we do it in Paris at Quantonation's offices, and here logistics is quite different. So try to get used to it, and it's a first, so bear with me. We'll have Jean-Philippe Piquemal from Sorbonne University talk about molecular computational drug design. It's the first presentation today. Josh Nunn and Richard Murray from Orca Computing from the UK will talk to us about optical quantum computing, and Karl Thibault from University of Sherbrooke in Canada. He will tell us about an initiative that students and the faculty have launched there on entrepreneurship, which is pretty exciting. I was there a couple of weeks ago. I think it's really interesting thing to hear about. So really the idea is that we've got academia, science, entrepreneurs, students in a way, pretty excited about the program and the lineup today. And the last, I will stop talking very soon. So last announcement, we'll have the next meetup in April 14th. Got the lineup already. Jean-François Bobier from BCG, Loïc Henriet from a startup called Pascal, and Simone Di Liberato from University of Southampton. So if you're interested, take note, and we'll broadcast that in a couple of days once we're final with a couple of things. So again, here are the ground rules for Zoom. Let's try to work this properly. Don't be afraid to ask questions. Questions are good, and we try to answer in due time. And of course, slides and video will be shared later. So without further ado, I'll let Jean-Philippe introduce himself and tell us about a very timely topic, obviously, computational drug design. Floor is yours, so to say.
Yep, thank you, Christophe.
So now we move to something completely different, still computing, of course, but we'll have Josh and Richard present to us their initiative. So optical quantum computing with a very scalable technology. So the floor is yours, guys. I've got more or less 25 minutes for that. Let's try to be in time. Thank you.
Great, thanks very much. Thanks for the introduction. Let me try to start this presentation. And maybe, can you hear me okay, everybody?
Yes, it's good.
Fantastic. Yeah, thank you very much for the invitation, Christophe. It's really, really interesting to present to everyone here. So the way we thought we would do this is, well, okay, let me introduce myself. I'm Josh Nunn. I'm the CTO of Orca Computing. And I'll talk for a little while. I was asked to give an overview of photonic quantum computing, which so my background is an academic, so it'll be a bit of a researchy overview, and then our CEO Richard will finish off the presentation and talk a little bit about the company Orca. So let me see if I can switch the slides. Okay, so. A very brief motivation for quantum computing, but we've already got had a fantastic introduction to that from the previous talk, which was, by the way, really interesting for me. So the exponential increase in conventional computing is in terms of putting more and more transistors on a chip is over by now, as you might have noticed if you've bought a laptop recently, and so massive parallelism is one way out of this, and of course quantum computing is another. Just in the previous talk there was some really much more in-depth statistics about the difficulty in computational chemistry for pharmaceutical R&D. This is sort of I've heard it jokingly referred to as Eroom's law, which is just the opposite of Moore's law, and there's an exponential decrease in the yield per dollar of drugs research. And so applications for quantum computing could be, of course, in that area. And there's another interesting area which is in logistics and so problems that aren't natively quantum, but have very complicated solution spaces that can be explored with a quantum machine. So there are many platforms for quantum computing that I'm sure many of you, if you have an interest, will know about. For example, there's silicon, trapped ions, diamond is an interesting platform. Superconducting circuits, of course, being taken forward by the big tech giants in the US. Neutral atoms is an interesting new, newly commercialized platform. So Pascal, the company that Christophe mentioned, will be talking next week, I believe, pursuing that approach. So the topic of this talk is photonics. So in photonics, it's fairly easy to see how you can produce a photonic qubit. I've drawn here the two black lines are a pair of waveguides that you can send light down. And I think we all know that light is made of particles called photons. So if you can imagine a single photon that's in one of the modes, you can make that, for example, a down state of a qubit. And if it's in the other mode, it would be an up state of a qubit. So we all know qubits have two states, and that's a way to make a photonic qubit. And so what we need is waveguides to do that. And there are lots of platforms for making photonic waveguides. This is one this is glass on silicon. And this picture here is an optical fiber. And so why would we want to do this? Why would we want to use photonics as a platform for quantum computing? Well, the optical carrier frequency of photonic optical signals is really high, about 100 terahertz. And what does that mean? That means two things. One, compared to all other types of qubits, photonic qubits can operate at room temperature in ambient conditions, and there's no need for cryogenics and vacuum systems. On the other hand, the system can support very high bandwidths. So and so you can really imagine the system running at the highest possible clock rates that you can run with electronic control. So up to hundreds of gigahertz are possible nowadays. Some other very advantageous aspects are that we have optical fiber, which is really an amazing technology. It's a kind of a quantum wiring. You can send quantum states down an optical fiber from one place to another, and you can connect them up in arbitrary ways. So there really isn't another quantum platform that has this amazing ability to connect with over distance. And that allows you to do things like networked quantum computing architectures. For example, superconducting qubits in different fridges could be connected optically. Trapped ion qubits in different traps could be connected optically. And you can imagine, therefore, making a modular system which is very easy to extend and scale up. So photonics is a really key technology for that. And this is an example. This is just an animation showing how you could entangle a pair of ions in different traps. This is just a selection of large research consortia that have been investigating this in recent years. So this is the top right is a US consortium, which is led to IonQ, the company IonQ. This is a UK consortium, which is actually based in Oxford, and that's actually where we span out of. And this is this QTech is a consortium in Delft in the Netherlands that have been working on diamond qubits. And so many of you might have heard of this idea of a NISQ machine. So NISQ stands for near term or noisy intermediate scale quantum computing. So that's where you don't have to build a full scale fault tolerant machine in order to get some computational advantage. And an early idea in that direction was this idea of boson sampling. And that's where it was discovered that if you send photons through a complicated waveguide circuit, then the statistics that you get on the other side when you detect those photons is provably it's computationally hard to predict. So that was a clue that there's something computationally interesting going on, but it wasn't really obvious what you could use this for. So more recently, there have been proposals to actually use these types of systems for quantum simulation of molecular dynamics. So clearly there's we heard a lot about molecular dynamics in the previous talk. The dynamics of a molecule involves atoms oscillating, and those oscillations are coupled to each other. Well, of course, optical fields are also oscillating. And if you send them into a waveguide circuit, then you can couple those waves together. So there's a direct mapping between vibrational dynamics of molecules and an optical system. which has led to proposals for using this for that type of simulation. And there's been experimental progress as well. This is a beautiful, that's what's on the, I'm showing you now is a beautiful picture of a silicon photonic chip that's come out of Bristol recently. And I'm just pointing out that there's a spin-out company from Bristol, which is looking to commercialize this stuff. And this was a recent result from Jianwei Pan's group in Hefei in China, where they really did an enormous boson sampling experiment. So 20 photons gives you a Hilbert space. So this essentially the configuration space of the system is 10 to the 14. So 100 trillion dimensions. It's very, very, very interesting. And I just want to flag up that the photons were provided for this experiment with what's called a quantum dot, which is a technology that's being developed in Paris by a company called Quandela. They didn't actually provide the dot for this experiment, but they're developing related technologies. So I thought that might be of interest. There's another way of looking at photonics, which is instead of thinking about photon particles, you can look at the electric field of light as being an oscillation. And there are two numbers that parameterize this oscillation you can write down. I've written them down here as X and P. It's the bit that goes like a cosine and the bit that goes like a sine. And there's an analogy here with like a weight bouncing around on a spring, in that the X is a bit like the position and the P is a bit like the momentum. And so in quantum mechanics, many of you might have heard that position and momentum are quantities that you're not allowed to simultaneously know at the same time. And in fact, the exact same is true in optics, is that the X and P numbers are actually numbers that you can't know simultaneously. So there's an uncertainty principle, just exactly the same as the Heisenberg uncertainty principle, that says that if I sort of plot my optical state on a graph of X and P, I can't draw it as a point. It has to be drawn as a kind of a blob, a sort of diffuse blob, to express that uncertainty. And then sometimes people talk about different shapes for that blob. So the simplest type of blob is a nice Gaussian blob. It just looks like a nice uniform hill. And then actually, if you draw the shape of the blob for a single photon, which you can do, then you get a very weird shape that sort of goes negative and looks a bit strange. So more recently, there's been an idea of doing boson sampling with Gaussian states, which are these states that can be drawn as a nice easy blob in X and P space. So these are some papers, and most recently, this is a paper from a company called Xanadu that some of you might have heard of. That's based in Toronto in Canada, and what they're proposing to do is to do Gaussian boson sampling for, there's a particular application in finding dense subgraphs with a machine learning application. Okay, but none of these are universal quantum computers. And so there's a challenge. The big challenge is that photons don't interact with each other. So of course they do in Star Wars. You can have a fight with Darth Vader and your lightsaber will bounce off his. But in reality, we know that if you send two beams through each other, they just cross straight through. So there's no interaction, there's no bouncing. And so how can I do a logic gate with photons if they don't interact? And of course, the answer is it's tricky. So you can make logic, but the way that you have to do it is using this idea of interference and measurement. So what's on the bottom diagram is some photons being brought together on a beam splitter, and then one of them is being detected. And in the case I get the right measurement result, then I get an effective gate. I get an effective interaction. And so this is a reason why you can't build an optical quantum computer yet. It hasn't been done. And it's because the measurements in quantum mechanics are inherently probabilistic. They don't always give you the answer you want. So your gates are not always successful. And this gives you a scaling challenge. So for example, suppose I have a gate that works with a chance of 1 in 10. If I put two of them together, now my success probability is only 1 in 100. And if I put 3 of them into a machine, now my success probability is just 1 in 1,000. So clearly that's not a scalable design for a processor. So what I'm mentioning here now, next, is one way to begin to circumvent this issue. So this is called measurement-based quantum computing. And so sometimes it's called one-way quantum computing or cluster-state quantum computing. And the idea is that what you can do is, instead of doing your gates sequentially one after the other, what you can do is build a very large entangled state first. So an entangled state is lots of quantum particles, lots of quantum bits, qubits, all correlated together in a large quantum state. And then gates are actually performed by making measurements. And there's a specific proposal for how to implement this with photonics. And so this is called ballistic quantum computing. And there's a nice diagram here, which is taken from this paper down here, where you can start with some small entangled states, which are called microclusters. You send them into a waveguide circuit, which is drawn here as a U. And then what emerges from that circuit, after you get some detections, is an entangled state that has inside it this desired cluster state that you need. So you have to search it out. You have to search the connections that give you the cluster state you want. And so the challenge is to build these small microclusters that are called GHZ states, and then try to build up this large cluster state as a resource. So this is just a neat animation that I got from Anthony Lane over in Bristol. And it shows you that you construct this state and try to forge links to give you the right resource for quantum computing. Okay, and some of you might have heard of SciQ, which is a company over in California that's pursuing this architecture. And I mentioned continuous variables before. There is a version of quantum computing using continuous variables. And so this is a proposal here to where you build, again, you build a large cluster state. The challenge here is that it only gives you a computational advantage if your states are non-Gaussian. And so I mentioned that there are Gaussian states which are easy to make, and there are non-Gaussian states which are hard. And it turns out that preparing the non-Gaussian states is also probabilistic. So there's no free lunch. There's a difficulty here. But okay, I wanted to flag up that some of these nice results are coming from Nicolas Trepp, who is really a world leader in this field, and he's based in Paris. So which would have been where we were all meeting if it wasn't for the end of the world. So what we really need to do to overcome this challenge is we need some kind of multiplexing. What do I mean by multiplexing? Well, what I really mean is that we need some way to overcome the fact that we have probabilistic measurements. And our solution to this problem is to use quantum memory. So a quantum memory is just a device that can store photons for some time and then release them on demand, just like in this little video. And if you can do that, it means you can try to create an entangled state many, many times, and you might fail, but when you succeed, you're able to store it. And if you can store it, then you can build up an ensemble of these states. You can build a collection of these states, all of which are waiting in the memories, and then you can release them together in order to do this ballistic quantum computing protocol. And so the last thing I want to mention is that we've come up with a scheme to allow us to implement that kind of storage. So we called it OFF-RESONANT cascaded absorption, which is a kind of a silly acronym, but it ends up being Orca. The idea is to take just a bunch of rubidium atoms in a box, in a cell, little vapor cell. And those rubidium atoms have a ladder of transitions in them. So they have a ground state, and they have an intermediate state, and then an excited state. And what we want to do is convert a photon into an excitation of this second excited state. So we do that by sending a control field, a very strong laser pulse into the atoms at the same time as we send our photon in that we want to store. And what the control field does is it causes the atoms to absorb our photon. And then at a later time that we choose, we can hit the atoms again with a second laser pulse, and that allows us to retrieve it. And so this is a way to produce one of these quantum memories. And what excites us about it is it's very technically simple. It works at room temperature. It's very broadband. We can store many gigahertz bandwidths. We can integrate it into fibers, and it's really completely noise-free and highly efficient. So that's really the basis for the company that we've span out. So this was my conception of what the logo should be: some kind of marine mammal with maybe a laser on its head, but we weren't allowed to do that. So this is Orca Computing, and I'm going to pass over to our CEO, Richard, now to talk a little bit more about the company.
Thanks, Josh. Really nice talk. Hello, everyone. Just to introduce myself. So I'm Richard. I'm the CEO of Orca. So I work alongside Josh. And my role is to try and structure Josh's research, world-leading research in this field, in the field of photonic-based quantum computing, into a commercial venture. So Josh, if you want to move forward a slide, that'd be great. Thanks. So just to summarize, where Josh was coming from, Josh gave a really nice overview of quantum computing and the opportunity for photonics in the quantum computing space. And just really give you a top-level view. Many of you will have heard of quantum computing. It was mentioned in the last talk. The challenge is really about scalability. So someone did ask the question, and I have a nice answer to it. A little statistic for you. If you want to model penicillin, you need 10 to the 86 classical bits, just normal bits. So 10 to the 86, that's more than the number of atoms there are in the universe in terms of bits. But if you were to build a quantum computer with 286 qubits, that would be able to do the same job of modeling penicillin. So it's pretty obvious, and there's pretty united view that given enough qubits, you can solve some pretty challenging problems. But the real challenge is how you get to of order hundreds or thousands or 10,000s of qubits. And the whole world seems to be stuck, maybe not permanently, or maybe permanently, around the sort of 50 qubit mark. So the groundbreaking work you've seen Google release and numerous others has been to announce quantum supremacy, which I won't argue is a hugely significant milestone for the field. But with 50 qubits, you are not going to be able to solve realistic problems like the previous speaker was describing. So we believe there is really a race to be the first commercial organization to reach have a model that can scale to hundreds, thousands, and tens of thousands of qubits. And we believe if you're entering this phase, you really need to think almost from scratch, and you need to be exploring new approaches. So what Josh described earlier is the approach towards the solution towards doing that with photons. And in particular, Orca has a very unique way of approaching photonic-based quantum computing that leverages Josh's previous work in these quantum memories that he described in his last slide. And what we've shown that it is possible to scale up the Orca architecture to one of these fault-tolerant lattices, which is an error-corrected quantum computing state. And we believe that the overhead, the burden of doing that, is less significant than the other competitors in that field. So although we are honest and open with the fact that we have a very small number of qubits now, we believe that we are a contender in the race to get to the world milestone, which is thousands of qubits. Thanks, Josh. Next slide. And I think also significant to Orca is the team we have backing us, behind us. So we have really excellent people on the technical side. So both Josh and our other technical co-founder, Professor Ian Walmsley, who's provost from Imperial College, but also myself and my other co-founder, Christina, who are steeped in experience on the business side. And, I have a technical background, but also a business background. And one of the things you realize about this field, if you come at it from a more commercial perspective, is that it is important to aim for early wins. And that is embedded in the company strategy and structure. So as Josh mentioned, we already have an Orca quantum memory device that's working in the lab. We have near-term milestones to build that into a deterministic photon source, which we believe could have early revenue potential, and one of these NISC early stage near-term quantum processors, which may have niche but potentially useful applications in the short term. And our strategy is to build on those towards these 3 qubit states, these GHZ states Josh mentioned. And if you're coming from a commercial perspective, you'll recognize the business model of sort of bootstrapping. You use your early revenues to support later stage R&D. And we believe that the sort of total journey, the capital investment needed to bring a quantum computer to market, needs you to take a sort of semi-bootstrapped approach towards doing this. And based on the hardware platform we have, which means that we can buy in a lot of off-the-shelf telecoms components, we're able to address this need of building a nearer term. I won't say it's near term, of course, but in the field of quantum computing, it is nearer term than other companies in the space at the moment. Thanks, Josh. If you want to do the next slide. So I mentioned, early markets and adjacencies. So some of the core components we're building within Orca, the quantum memory device, the photon cannon, which is a deterministic single photon source. So for sort of the lay people in the audience, a device that spits out very high photons on demand. These are devices which don't exist currently. And so our strategy is to attempt to generate early revenue streams through trying to sell off some of those components into adjacent markets. And if you're wondering how we're going to do that, our business strategy is to very much not distract ourselves from the core mission of building a quantum computer. So we'll look to do that through distributors. Thanks, Josh. Next slide. So I've mentioned a little bit on the team already. It is something that I personally think is incredibly important and quite unique to Orca. So we really do have a strength in the diversity of the team. So I mentioned them before. Here are some mug shots. So you see Ian Walmsley there, who's more than a decade in the quantum optics space, leading quantum optics. Josh, who's been leading quantum memories and optics in the UK, and 2 really excellent technical early hires joining the team. And then with the likes of myself, so I used to run the UK Quantum Technologies Programme for UK government. So I invested something of order £50 million in the quantum technology scene back in 2013, and really, and my co-founder Christina has an MBA and a background in finance from DE Shaw. So you can hopefully gather from the sort of team that I'm describing that we are a team that can approach quantum computing from a highly expert technical side, but also a side that knows how to build a proper business from it. And this space, from looking at this space, and if you've had experience looking at this space, that is quite a unique mix, and it allows us to look at quantum computing in a pretty unique way, I think, and structure our approach differently. Thanks, Josh. Next slide. So a little bit, and I realise this is very business focused for a scientific sort of conference, but a little bit on our progress today. We've been really lucky, really successful. We've raised a little bit of venture capital money, $1.6 million, to help us get to our first technical milestones, the photon cannon and the NISC machine. We've managed to be very successful in leveraging non-dilutive government grant funding. So there's a lot of that in the UK at the moment, and we've been successful in winning $1.1 million, and that will continue. We've hired 2 engineers and we filed 3 patents. And what I hope is that this is an introduction to you about some of the work we're doing in Orca. I really do hope and believe that over the next 18 months we'll become a leading player in this quantum computing scene. So this is where we're starting out from. Okay, thanks Josh. So then there you go. There's the sort of summary slide. So I suppose a few take homes. So we are looking to do quantum computing and photonic based quantum computing in a quite a unique and quite attractive way. It's all possible through Josh's research, so proprietary Orca memory technology, which is patented and owned by the company. It does leverage plug and play telecoms components, so there's pretty much hardly any very bespoke, expensive equipment. We think we've got a world-class team, both on the technical side and the business side. And we do have a capital efficient business model due to the leveraging grant funding that were mentioned, early revenue streams, and the technology just being, well, simpler and cheaper in the long run. So here you go. That was my pitch. I hope that was interesting, as well as Josh's talk about the technology. Really, if you do have any questions, please don't hesitate to reach out and contact us. Really looking forward to talking to you.
Yeah, thank you. Thanks, Josh and Richard. Great presentation. Appreciate very much. So much so that we invested actually also into the company. So we're among at Quantum, we're among the first backers. I mean, we like that very much. And I think it's going to be a great.
Much appreciated.
Thank you very much. Thanks, Josh. Okay, so now we're coming to our third talk with Karl. Yeah, Karl is here, talking about a great initiative from University of Sherbrooke, Institut Quantique. So I was there, I think, twice already. So I saw how powerful the ecosystem was, and I thought it would be a really good idea to share what Karl and the team have done there. I think in the sense of building a great ecosystem, and I think also it's important that the meetings that we have in the lab is. The Lab Quantique is not only about the science, but also about initiatives such as this one. So, Karl, floor is yours.
Yes.
That's slightly less time than the others. Sorry for that, but let's try to give you 20 minutes. Thank you.
I'll try to make it quick. All right. So, can you all see my screen?
Yes. Good.
All right. Great. So hi everyone. So first of all, I'd just like to thank Christophe for organizing this wonderful event and for inviting me to talk to you a little bit more about what we do here at the Institut Quantique. So I'll introduce myself. My name is Karl Thibault. I'm the program manager of science and entrepreneurship here at the Institut Quantique, which can be translated to Quantum Institute. And I've titled my talk "A Focus on Student Empowerment," and I really hope that by the end of this talk, you have a better idea of why this is important for us and how we've made this our focus at the Institut Quantique and the results that it has given us. So at the Institut Quantique, our mission is to place students at the center of research in an open and collaborative environment to accelerate the transition from science to quantum tech. We train leaders who have the skills and critical thinking essential to creating knowledge relevant to a changing society. And you'll see that for me, the two main parts of this mission here is the students taking the science to quantum tech. And I hope that, again, by the end of this talk, you'll see why. So a little bit on the research side here, just to go over quickly about what we do at the Institut Quantique. So first of all, we have an axis of research about quantum materials, where we do a lot of experimental research on growth, deposition, and characterization inside large-scale facilities. And we also look at the properties of quantum materials on the theoretical side using high-performance quantum computing. Second, there's also quantum information. Here again, experimental and theoretical side, looking at different types of solid-state qubits that were mentioned by Josh, such as spin qubits, impurity-based, NV centers, and superconducting qubits. And on the theoretical and also experimental side, we look at quantum algorithms and quantum error correction schemes. And the third axis that we focus on is quantum engineering. So looking at the development of key quantum devices such as sensors, photonics, and electronics in the cryogenic setting, and looking also at the creation of specific devices that can be used, such as single photon detectors and emitters. And so our key strength at the IQ is definitely that we have these three axes working together and interacting in the same space. And this is something that's not present in a lot of places in the world. There are few key places that have all of these three expertise working together. So we're quite happy to have that here. But the Institute is first and foremost people. So there are 26 professors that have more than 150 graduate students and postdocs working with them. And we also have 22 research staff that making sure that the labs work smoothly and that we keep the expertise on these state-of-the-art equipment and infrastructure over the long term. So we don't do this alone. We have many partners. Our number of partners has more than doubled since the inception of the Institute in 2015. We have quite a wide range going from corporate partners, private industries, governmental labs, other public institutions. But more importantly, we're also trying to build a local ecosystem around the Sherbrooke area, which is called the Eastern Townships. So it's important for our members to have access to jobs here in the area when they graduate, so that we don't export all of our good talent. So one good example of this ecosystem that we have is the 1Qubit Vancouver startup, which has opened an office last October here in Sherbrooke. So the story of this is their CEO came here and he talked to our students, and he basically directly asked them, so where should I open my next office, here or in Montreal? We're looking to do something in Quebec. And the students basically told him he should open it in Sherbrooke, and so he did. So that's great. We are also, we will be, or we are now, it's quite in the making, the 11th, if I'm not mistaken, IBM Q Hub. And lastly, the city of Sherbrooke itself has deposited a proposal to the government of Quebec for a so-called innovation zone directly in quantum technologies. So things have started moving very quickly in the recent past, and we are very happy about that. So as I said on the previous slide, it's really important to not export all the good students that we train here at IQ. And one simple reason for that is the shortage of talent in these high technology sectors. So as you can see here from an excerpt of the New York Times a bit more than a year and a half ago, at that time they estimated that there were only 1,000 or so researchers that could really be experts in quantum computing. Now that number is quite low, but if you think about only senior researchers, I think it's a good estimate. And if you compare at the AI field, which has been in shortage of talent for a while now, there's about 25 times less people in quantum which are experts by their estimation. So it's really important to keep the talent. And for us, that's why we strongly believe that beyond developing that quantum technology, the biggest advantage today in the field is the talent. And so here's what we do at IQ to support our talent. So the first example of this is the seed funding program that we've ran since 2016. And the seed funding program has been open to all of our members. So typically, such programs and research institutes are open for professors only. But from the get-go, we've decided to open this to all our members, including students, technicians, research staff, everyone. And they're all reviewed by the same committee under the same rules. And you can think about the first year when student programs were funded and professor programs were not. More than a few eyebrows were raised. But since then, I think it's become quite clear to everyone why we do that and the benefit of doing that, as you will see. We also support student-driven initiatives and student entrepreneurship. I'll go into this deeply in the next slides. And we also do our best to provide the best training opportunities in quantum science for the talent that we have here. So one example of this is a new master's program, which is called QSciTech, which is part of the CREATE program of the Government of Canada. And in this program, we're trying to take the same tradition from the University of Sherbrooke of hosting co-op programs or internships in industry during your studies. And this has been true for a lot of programs at the undergraduate level at the University of Sherbrooke. And this program tries to take this and put it also in the master's program. So every master's in this program will do an internship at one of our industrial partners. We also have a wide range of backgrounds in this program. So people from engineering, people from physics, and they all exchange courses. So people from physics do engineering courses and vice versa. And then they all come together and do entrepreneurship course. So this is a quite new program that's really exciting. And we're also in the making of 2 other programs. So another master's in quantum science and tech and an undergraduate program in quantum science which we hope will come live pretty soon. All right, so moving on, I'd like to focus a bit more here about a certain student initiative in particular, in which Christophe here has participated in the past. So talking about this, I need to go back a little bit in time. So in 2018, one of my colleagues, Augustin, came to me and said, you know, Karl, I'm building a team to determine how to foster entrepreneurship mindset and startup culture at the IQ. And the IQ was endorsing him at the time, and they actually wanted us to create a plan for them of how to do that. And this initiative came to be known as the Q2 initiative. So I said yes, and Augustin put together a team of 10 people. 8 people were from the physics department, so the 8 people that you see in the middle here. There was 1 person from management school on the left, Adam, and 1 person from the communication side, Vanessa. And together, we started on a premise that I told you before, which is that the deep tech physics startup and entrepreneurship were not really part of the culture before the IQ. And we really tried to determine the why and to create a plan for the IQ to move forward with that in the future, to foster this mindset. And so one of the key issues that we found is based on the assumptions that students have about their future. So this is something that's been known for quite a while. So if you look at this 2015 Nature study, for example, they asked students and graduate students in science in general how they think they are likely to end up in academia after their studies. And more than 60% of students actually think it's quite likely that they'll finish in academia. And only about 30% of them think that it's not likely that they will. And you know, during our project, we found out that this is basically the same in Sherbrooke also. But the reality is actually basically the exact opposite. So if you look at the graph on the right here, you can see that, so this is new physics PhDs in the US from 2011 to 2016. You see that it's the exact opposite. Less than 20% of graduates finish in the academic field, and the others end up in the private sector or government or whatever. And on the graph on the left, you see that actually most of them don't even do physics after their graduation. And this is also the same at the IQ. So these are the stats for our last 3 years. We see that about 20% of our students end up in academia, and the rest don't. So this is the position in which Q2 tried to put itself. So Q2 really tries to be in the middle of the students and the job market. And knowing this clear difference between the assumptions of the students and the reality of the job market, we came to the conclusion that Q2 should be a Students for Students initiative that aims to steer the graduate training towards a better student job market fit. And we do that by providing assistance, support, and information on employment in the quantum technology sector in Quebec and elsewhere, by creating links with the industry, and by promoting entrepreneurship at the IQ. So it's important to emphasize here that not finding a job in academia at the end of your studies should not be seen as failure. And every other alternative careers can be extremely fulfilling for all of our students. And I think that providing support information on the reality will also help in that. So the main action that we have put forward so far is the creation of a new series of seminars or activities in which we let students invite people that they want to see give seminars that come from alternative careers than academic one. And then we let the students organize these activities around that alternative career to show their peers what could be possible paths for them. And here I just want to emphasize that in science departments, seminars are basically 100% of the time given by people from the academic field. So these students barely ever see role models from other spheres. And this is really one one thing that we're trying to change with this series. And this is one of the reasons we think that there's such a big discrepancy between the assumptions for their future careers that students have, for example, and the reality of the job market. So the first people that we invited with Q2 for this were two persons from Zapata. So there was Alan Aspurukutik, which is actually a professor at the University of Toronto, but since he had such a varied background, it was really informative to have him at that series. And then we hosted Pierre-Luc Dallaire-Demers from Zapata, which is a researcher with a physics background. And next in last December, we had Nick Farina from EuroQ, which is an entrepreneur who does not come directly from physics. So he had also a different take on what could be possible careers and how to see their future for students. The first activity of this year, we had Christoph, our host of today, which has a physics background, but is now in investment. So that also gave a different take on their lives to our students. And the last two activities that we had, so one in February was a bit different. It was about help resources at the University of Sherbrooke for students, more on the mental health side. And the one that was supposed to be actually last week was canceled, unfortunately, due to the current situation. But it was with CDL, Toronto and their alumni, and the Quebec Quantum Incubator Consortium. So unfortunately, as I said, it had to be canceled, but we really hope that it'll be done really soon as we can after this situation. And so this series has been really eye-opening for a lot of our students, and it also provided CUDA members opportunities to interact with these people, organize these events, broaden their skill sets by interviewing them and thinking about what to convey to their peers in these activities. So this has been a great success so far. And culture change is really slow, but we've had some great movement here, great effects here at the IQ already. So there's been a surge in patents, 17 patents since 2015 coming from the IQ. There's been a license that has come and been given to a private company, Quantum Numbers Corp in Montreal. And we've had 4 startups in the past 4 years that have emerged from our physics departments, which are all part of IQ and are all led by ex-students. So 3 of them, so the 3 on the right here have been funded in the last year. Some of them stem from the seed funding program that I described earlier. Some of them come from ex-Q2 members, such as Augustin. And this might not seem like much for startups, but in this field, it's actually a lot. And coming from a physics department, which had basically no startup culture before, we think this is a great achievement. So we also have an entrepreneur in residence program, which we've built up with the 2 accelerators here at the University of Sherbrooke, the AED and the ESSET. And some of our startups are right now running a pilot run of this. We're really hopeful for this. We're looking forward to see the results. And we hope that our startups really, we can give them a head start with this program. So that's it. I'll leave you with the team. So this is the current team at Q2 and how you can reach us on Twitter, on email. We'll be more than happy to host you, the Institut Quantique, if you come after the current situation. So we keep in touch with that. And the key message that I'd like you all to remember today is that empowering students by letting them, for example, invite who they want to see, organize activities, think and work on specific issues that's related to their studies or careers is extremely powerful. It makes a major difference in the skill sets that they own when they leave your institution. It prepares them better for their careers, and it's also really good for your own institution. Students don't necessarily want to see the same people that your professors want, so it makes you interact with people in the community that usually you would not see if only professors were inviting people. So it's really interesting, and it's been great for us. So thank you for your time, and I hope that if you have any questions, I can answer them.
Christophe, we don't hear you.
So thank you, Karl. Thank you very much for the presentation. I think it was great to have you. I'd like to thank everybody actually at this stage. So Karl, Josh, Richard, Jean-Philippe. I think it was great for this first online version of the meetup. Pretty happy also to have people from all around the world. I think it's a plus, definitely, that everybody can come to Paris to our events, obviously. So thank you very much. If anybody on the attendees has questions or anything like that after this session, I think you can connect with us and all the panelists on the meetup page, or I can provide, or just, find a way to chat with us through Meetup or elsewhere. I'd be happy to go on with a discussion there. So I'd like to show just before finishing. So the announcement of our next meetup. So it will be April 14th, as I said earlier. Try to have also free presentations. Simone from University of Southampton as an academic, Loic at Pascal, a startup, and Jean-François at Boston Consulting Group. Would be interesting to have a mix of talents such as this one. I think was a great tonight. Come back. I would like you to have for the next time. And I look forward to great sessions. And obviously, it would be better to see you all in person here in Paris. Hope we'll have the pizza and the beer next time. So many people asked me about that in the last 30 minutes, or to give me some comments about this. And I think it was funny, but yeah, actually it's true. Looking forward to see you for the next session. Thank you again. Thanks to our panelists. Bye-bye.
Bye. Thank you.
Yeah, thank you.
Thanks, Christophe. Fantastic. Thanks. It's great.
Thanks. Bye-bye.